Year 13 short revision video number 16. So it's very clear from the image in the question that we have a normal distribution here, and we're told that x is a continuous random variable which is normally distributed with mean mu and variance sigma squared. So the area of each of the unshaded regions underneath the curve is 0.025, so that's quite useful. So we know that the tails are symmetrical. The lower boundary of the shaded region is at 16.452 and the upper boundary is at 21.548. So for part 1 we have to calculate the value of mu. Now mu we know is in the centre of the distribution, so we can use the fact that everything is symmetrical to find the halfway mark between 16.452 and 21.548. So add them together, halve that will give us our value of mu. So that's a value of 19. It does look like 19 from the sketch graph, but this gives us proper confirmation of that answer. Now for part 2, to calculate the variance, we're going to need to use either one of the tails. We know that the probability that x is greater than 21.548 is equal to 0.025. Now I'm going to standardise this to the z distribution. How do I know that we need to standardise? Well, we don't know the value of sigma squared. If we don't know mu, or we don't know sigma, or we don't know either mu or sigma, it's likely we're going to have to standardise the whole thing. So converting to z, that's the probability that z is greater than 21.548 minus mu over sigma, and that still equals 0.025. So we now need to use phi minus 1 to find out the value corresponding to the position of 21.548 on the z-axis. So using phi to the minus 1 will give me 21.548 minus mu over sigma, which is our z value. Now, how do I use phi to the minus 1? Well, I always go into stats mode on the calculator. To do this is a little bit more obvious as to how to go about this. From there, we need to choose the option for distribution, or dist, which is F5. We then want the normal distribution, which is F1. And we want the inverse normal, which is F3. Now, the options that we have there, we need to make sure we have variable. Now, our tail is going to be the right-hand tail because we're working with this region over here, which is on the right-hand side. So that's the right tail. And the area is the probability associated with that tail, which is 0.025. So all of this needs to be set on our calculator. And we're then asked to enter the value of sigma and the value of mu in that order. Now sigma is 1 and mu is 0 because we're working with the z distribution, which has a mu value of 0 and a sigma and sigma squared value of 1. So inputting all these values in very carefully then gives us the inverse phi value, which is 1.9599, and that's equivalent to 21 minus 548 minus mu. Now mu, of course, is 19, so this then tells us that we've got 2.548 over sigma equals 1.9599, and we can rearrange this to get our value of sigma. So sigma equals 1.3000 ... And the question actually asks for the variance, so we need to square this value to give us 1.690 ... So 1.69 to 3 significant figures is the value of our variance, sigma squared. Now, part 3, we're introduced to a new variable, which is a function of x. So y is equal to 4x plus 5. We need to write down the distribution of y. Y will also have a normal distribution because it is a function of a normal distribution. So y will also be normally distributed. And what we have to do is find the mean and the variance. Now, the mean of y is going to equal 4 times the mean of x plus 5. So that's going to be 4 multiplied by 19 plus 5, which comes to 81. So the mu value for y is 81. Now, we then know that the standard deviation of y is going to equal 4 times the standard deviation of x. Remember, this plus 5 here does not affect the value of the standard deviation. So this question is all about linear coding and how you can code a variable to turn it into a new variable, and how this affects the mean and the standard deviation, and what the mean and standard deviation of the original value are compared to the mean and standard deviation of the new variable. So the standard deviation of y will be 4 times 1.3000. So that then gives us a value of 5.2002 ... So let's say 5.20 to 3SF. So the distribution of y I can write has a standard deviation of 5.20 or a variance of 5.20 squared. So if we wanted to write down the variance of y, that could be calculated. It's the square of 5.2, and that comes to 27.042 ... So 27.0 to 3SF if we want to give the variance of y. Now, the last part of this asks us to work out for 1 mark the probability that y is greater than 90. So we go back to stats mode again, distribution again, normal again, but this time we want to use the NCD, normal cumulative distribution option, which is F2. And we want data to be set at variable. For our lower value, well, we're doing the probability y is greater than 90, so we want the lower value set at 90. The upper value just needs to be a reasonably large number. I've entered 1,000 in here just to be sure. And we then enter sigma, which is our 5.2002 ... value. And mu, of course, is 81. Be careful to enter sigma and mu the correct way round, in the correct order. It's sigma first on the calculator and then mu. It is clearly listed, but it's an easy place in which people make mistakes and sometimes swap mu for sigma. It's also important that we enter the value of sigma on the calculator and not the value of the variance sigma squared. So the mean is 81. That's everything entered, and this gives me a probability of 0.04175 ... So I'm going to round that to 3 significant figures to 0.0418, and there's our final answer. It might be worth finishing off with a quick note on linear coding, because it is something that people do sometimes forget. So if x has a mean mu and a standard deviation sigma, if y is equal to, let's say, a times x plus or minus another value b, y is a linear transformation of x. Linear because we're just multiplying x by a particular value, then adding or subtracting another value. The mean of y would equal a times the mean of x, which is mu, plus or minus the b value. So you can see the relationship there. The standard deviation of y would equal a multiplied by the standard deviation of x, which is sigma. But again, as we mentioned previously, this part here does not affect the standard deviation. So the plus or minus b does not affect the standard deviation or variance of y.